Our next speaker is Dr. Ehsan Farahbakhsh. He's a research associate in the Earthbite Group School of Geosciences at the University of Sydney. He holds a PhD in mining engineering, mineral exploration from the Tehran Polytechnic. Welcome.
Thank you. Well, hi everyone. Well, today I'm going to talk about the novel framework that we have recently developed for extracting tectonic lineaments using remote sensing data and machine learning. And I have a co-author, Professor Dietmar Muller, that I think is watching us online now. So if you're there, Dietmar, hello. And well, before I get into the actually our framework and go through the different steps that we have in there, well, let's see how we can, use this framework and how actually this framework can help us to map, prospective zones of critical minerals. And as you know, and as also others mentioned in their slides and presentations, critical minerals, as you know, is the buzzword of these days. And both actually critical minerals include both metallic and non-metallic minerals, and they play a significant role in modern technologies, economies, and also national security. And also these minerals are widely used in low carbon emission actually technologies, and also they play a key role in electric vehicles, wind turbines, solar panels, and also rechargeable batteries. And as you know, each country and even each state has a specific list of critical minerals. And there are actually, Australia has listed 26 different minerals as critical to the country. And even NSW has its own list of critical minerals as well. And so Sabine also showed that graph. So yeah. As you see that, as the technology advances, more and also diverse critical minerals are needed in different technologies and in advanced technologies. And here is also another, interesting table that shows, for example, in the wind turbines and also in electric vehicles, you can see the diversity of the common minerals and elements that we need actually in these, technologies. So we need, to develop, some new methods to process the data that are available. And here is a map that shows, significant mineral occurrences throughout Australia that are rich in critical minerals. And the thing that here is, important, to us is the mineralization types that we have. And the thing is that tectonic lineaments, including faults, shear zones, all of these, features, they all play a key role in forming such mineralization types and such mineralization mineral deposits. And current, the mineral prospectivity maps that have been, developed in in recent years, they're mostly based on mineral systems approach. And so what is the mineral systems approach? We have 5 different components in the mineral systems, which is we need an energy source, and then there is the transport mechanism, and then we have trap, and then deposition happens, and at last we have preservation. So as you can see, each of these components has mappable criteria, and also we have spatial proxies actually to create different features or evidential layers that later they are integrated together, and that then we get a prospective map of our target commodity and also our mineralization type. And tectonic lineaments or faults, that include faults and others, they're only one of the evidential layers that we use in mineral prospective mapping. And they are later used to be integrated with other data layers that we have. The framework that we developed a few years ago, actually we tried that in a region in Western Australia, in a small region in Western Australia in the Capricorn Origin, in the west of Capricorn Origin, in the Gascoyne province actually. And this region actually is a mineral-rich, portion of that region. And here is the framework that we actually developed for extracting the tectonic lineaments, and here is actually the upper part of that. And the input to these frameworks, it can be, any optical remote sensing data. And as you know, remote sensing data are categorized into radar datasets and also optical datasets. And there are different platforms to acquire such data, like satellites, drones, even a sensor on a tripod. We can use that to acquire remote sensing data. The dataset that we used in this study is Landsat 8, and it's a multispectral dataset. And we used, actually, according to the level of the dataset that we have, we can apply different corrections, correction methods like radiometric corrections and also geometric corrections prior to actually processing that. This stage is called pre-processing. So prior to processing and applying machine learning methods to that, we do some pre-processing, and then we have used the dimensional introduction methods to actually convert our multi-dimensional dataset into a single grayscale image. And later we applied edge detection, methods to that. And in this study, we compared 3 different dimensional introduction methods. As you know, dimensional introduction methods are a subset of machine learning methods, and there are 2 categories for these, type of machine learning methods. One is feature extraction, and the other one is feature selection. These methods that you can see here, principal component analysis, independent component analysis, and also minimum noise fraction, they are all feature extraction methods. And our goal is to separate the significant part of the information from the insignificant part of the information. So we compressed all the spectral bands that we had in Landsat 8 data into a single grayscale image. And then to reduce the noise of the data, we applied 2 different filters to them, including an adaptive filter called Lee filter, and also another filter called median filter, to remove the noise from our data. And later we applied convolutional filters to our dataset, and the convolutional filters, they actually replace a pixel value with the actually average with the weighted average of surrounding pixels of each pixel. And we actually here, in addition to comparison of different dimensional reduction methods, we also compared the efficiency of 2 different convolutional filters, Laplacian and directional filters. Directional filters are known as the first derivative filter, and Laplacian filter is a second derivative filter. And later we applied our edge detection method to it, which is the canny edge detection. And canny edge detection is actually based on the squared gradient magnitude. And here you can see the grayscale images that we obtained by applying different dimensional reduction methods. And we applied edge detection methods to these 3 grayscale images. And here you can see, these are the output components of these dimensional reduction methods after applying all the filters that I mentioned, except the convolutional filters. And here, to see which dimensional reduction method is the optimum one, and we actually designed different profiles throughout our study area. And here, for example, you can see one of these profiles and also the signals that we got. And according to these, graphs that you can see, we actually concluded that minimum noise fraction is the best one. Why? The reason is, that the peak values that you can see in the minimum noise fraction plot is correlated with the tectonic lineaments that have been mapped by the Geological Survey of Western Australia. So this behavior of the mineral, the output component of MNF or minimum noise fraction actually made us to choose this method as the optimal one. And later, we applied, convolutional filters, to the output of the MNF method. And in figure A, you can see the output of the output after applying the Laplacian filter to the MNF component. And also we applied 4 actually directional filter in 4 different directions. One is in north-south, and the other one is east-west, and also northwest-southeast, and also northeast-southwest. So here we have 4 different actually 4 different grayscale that have been created using by applying directional filters. And it has actually, enhanced, tectonic lineaments in different directions that I mentioned. And here is the second part of our framework. And actually, after applying, edge detection, which is the CANI detector, and also later we applied the line extraction method. The line extraction method that we apply, actually the thing that they do is they connect, the edges, and they create a line out of the edges that we have created, or enhanced using the edge detection methods. And using the line extraction methods, we created a lineament map, but it is not yet a tectonic lineament map. And the thing that I should mention is that there are a lot of, parameters, while you're using CANI edge detection, and also pixel connectivity edge linking method. And we did a lot of, trial and error, and we did a lot of experiments to actually do some sort of parameter tuning and find optimum values for these parameters. And later, we mapped the streams that we have in the study area to convert, our lineament map into a tectonic lineament and remove those streams from our lineament map. Since the streams are, the most important natural, linear feature that we have in our study area, and we had to remove them from our lineament map. And it is noteworthy that in addition to streams, we also have roads and also other features that we need to remove them from our lineament map prior to actually creating the tectonic lineament map. And we did this using all the available maps that we have from the study area. And so here you can see the result of, actually applying this framework. And on the left side, you can see the tectonic map, which has been resulted by using the directional filter, and on the right side you can see the result of applying the Laplacian filter. And as it is obvious, you can see that the number of tectonic lineaments that we have extracted using the directional filter is much more than Laplacian filter. But the thing is that those lineaments that have been extracted using the Laplacian filter, they are more correlated with those that have been plotted or mapped by the Geological Survey of Western Australia. But on the other hand, you will see that the map which has been created using the directional filter, it is more correlated with the mineral occurrences in the study area that are related to the hydrothermal fluids. Here is the rows diagrams of these maps, and the upper 2 rows diagrams, they show the result of on the left side you can see the result of applying directional filters, and on the right side you can see the result of applying Laplacian filter. And here in figure C you can see the result of which has been obtained by the map of the Geological Survey of Australia, which have been provided by the Geological Survey of Western Australia. And the comparison of them shows that the azimuth of the major strike in all of these maps are similar to each other. But there is we didn't see any minor strike in the map which has been created by the Geological Survey of Western Australia. So this was the biggest actually thing that we realized based on these rows diagrams. And here actually we mapped the density of the tectonic lineaments that we have actually mapped using this framework. And also we draped the mineral occurrences that we have in the study area, and they are somehow related to the hydrothermal fluids and also the fractures in the crust. And the comparison of them shows that, as I mentioned, that the result of applying directional filters, and the map that which have been created using that is more correlated with the mineral occurrences that we have in the study area. And some of them, for example, pegmatites, they host the lithium, in the study area. And we can say that using this framework, we can create a reliable evidential layer for tectonic lineaments in the study area, which can be integrated with other layers that we have. And also in the graph, you can see based on the area under the curve that we have, we can see that it also confirms that the directional filter, shows more correlated results with the mineral occurrences that we have. And to summarize, I can say that as you see, as you saw, there are different steps in our framework for enhancing and mapping the tectonic lineaments, and the extracted tectonic lineaments using the combination of MNF and also directional filter, they result in a map that which is correlated with the mineral occurrences that we have in the study area. And the CANI edge detector and also pixel connectivity edge linking algorithms, can be considered as reliable methods to map tectonic lineaments. And irrespective to the actually applied dimensionality reduction methods and convolutional filter, we observe that both filters that we applied, they somehow are correlated with the GSW tectonic lineament map. And we conclude that the tectonic lineaments which are extracted, and particularly the directional filter, using the directional filter, they're correlated with the hydrothermal mineral occurrences in the study area. And we actually concluded that this, as I mentioned, the output of this framework can be integrated with other data layers that we have in the study area to map the prospective zones for hydrothermal mineral deposits and also critical minerals. And the incorporation of various sources of data, such as other geophysical data sets, can help us to improve our output. And it is noteworthy that with some slight changes, some minor changes to the framework, it can also be applied to magnetic data as well, since we can also use edge detection methods and apply it to magnetic data and also other other kind of geophysical data to map tectonic lineaments using them. And since in the regions that we have a thick layer of regolith, so remote sensing data cannot help us that much, so we need to use magnetic and also gravity data to map the structures that are in depth. And the other thing is that we can even in future, we are planning to replace the CANI edge detector and also the pixel connectivity method with more advanced machine learning methods like convolutional neural networks to map the tectonic lineaments. And if you're interested in this framework, you can refer to our paper, which has been published in International Journal of Remote Sensing. And also here is my email. And thank you for listening.
Thanks, Ehsan.